It's my great pleasure to announce the friend of the family, Tyler Ellison, who will give a talk on a topic that's also a friend of ours, and namely Floquet codes. And he will add a twist to this by talking about Floquet codes with a twist. So thanks for electronically coming to us, and we're looking forward to your talk.
Yeah, thank you. Thank you for the invitation to be here. I'm excited to share our recent work on Floquet codes. I'll be discussing a project that was done in collaboration with Joe Sullivan. He is a postdoc at UBC in Vancouver, and Arpit Dua. He is a postdoc at Caltech. Let me begin this talk with the main punchline. Maybe. There we go. So here's what I'd like you to take away from the talk. Floquet codes are a new class of quantum error correcting codes that are inherently dynamical. The code space evolves in time according to a periodic schedule of non-commuting measurements. In our work, we developed a new method for storing and processing quantum information in Floquet codes by introducing point-like irregularities to the code called twist effects. Here are the twist effects. I've marked them with a yellow X. We created these twist effects by condensing fermions or proliferating fermions along one-dimensional paths. So this is everything I'd like you to take away from the talk. At this point, you should feel free to scroll through the website formerly known as Twitter. In the remainder of the talk, I'll say the same thing, but much slower. So because I've been told that this is the quantum error correction subgroup seminar, I'm going to keep the motivation brief. Hopefully, I don't have to say too much to motivate quantum error correcting codes.
Yeah, cool.
That's right. That's right.
It's so brief that I didn't even finish writing motivation here.
Let's still digest this one. But yes, I think you don't have to introduce error correction. That's right.
Okay, cool. Well, just to set,
we're still a sub crowd for like summer conference reasons or so, but never mind. Okay, yes, I think I'm getting it.
Okay, cool. Just to set the scene, it's early for me, so maybe just to remind myself of what's going on. We know that quantum computers are susceptible to noise from the environment and faulty operations. This can inadvertently corrupt information while we're doing computations. So to make our computations reliable, we need to encode that information redundantly using a quantum error correcting code. There are quantum error correcting codes on the market, which have been highly optimized, such as the toric code, the color code, certain bosonic codes. But given the importance of quantum error correction, it's valuable to nonetheless keep exploring the space of quantum error correcting codes in the hopes of improving error thresholds, reducing computational overheads, or just in general finding quantum error correcting codes that are better suited to our current hardware. Now, unfortunately, I included a cartoon here, and I'm a little embarrassed about it, but I have to show it just to get to the next slide. So yeah, here we are exploring the space of quantum error correcting codes. And the next slide. Here's the plan for the talk. I'd like to tell you about twist effects in a particular Floquet code, which I'll refer to as the Z2 Floquet code. To get there, I'll first say some comments. I'll first remind us all about twist effects in the toric code. To do that, I'll review the toric code and describe the conventional method for constructing twist effects. Then I'll introduce a new method for building twist effects in topological code, such as the toric code, and that's via condensing or proliferating anyons along a one-dimensional path. Then it'll be pretty straightforward to create twist effects in the Z2 Floquet code. I'll review the Z2 Floquet code and then show that by proliferating emergent fermions, we can build twist effects. I'll conclude by commenting on some work in progress. Before I move on and say something interesting, let me make sure to encourage questions throughout the talk. To paraphrase a recent talk by Steve Gervin, I'm more interested in uncovering as much material as possible rather than covering as much material as possible. So please don't hesitate to interrupt me if something's unclear. naive questions are especially welcome. And if you're unsure of whether you should already know something, just ask. Okay, with that, as promised, let me discuss twist defects in the toric code. Now, most of you in the room probably know toric codes much better than I do. So we can just think of this as setting some conventions. I'm going to be working with an unrotated toric code. So we have a square lattice with qubits on the edges. There are two types of stabilizers, the generators of the stabilizer group. I'll refer to this one as the vertex stabilizer and this as the plaquette stabilizer. I'll use a convention that the vertex stabilizer is a product of poly X operators around a vertex, and the plaquette stabilizer is a product of poly Z operators. Where do we store quantum information? Well, we store quantum information in the code space. This is the subspace of states, which are mutual +1 eigenstates of these stabilizers. Just to save myself some time and to absolutely no benefit of you, I'm going to change notation slightly. And instead of writing X and Z on the lattice, I'm going to represent poly X operators by red edges and poly Z operators by blue edges. This is potentially because of my background in condensed matter physics, but I think it's most natural to talk about the toric code and error correction in the toric code and twist defects in the toric code in terms of the underlying anyons. So let me just recall what anyons are in this context. In this context, anyons are violations of stabilizers that cannot be created or destroyed by local operators. There are three types of anyons in the toric code that I'd like to point out. The first I'll refer to as the E anyon, and I'll take the E anyon to correspond to a violation of a single vertex stabilizer. A pair of E anyons, can be created by a string operator composed of a product of poly Z operators along the path in the lattice. Likewise, M corresponds to a violation of a plaquette stabilizer, and this is created by a product of poly X's along a path in the dual lattice. And finally, you can put these two together. It's creatively named the EM anyon. This corresponds to a violation of both a plaquette and a vertex stabilizer. This is created by a string operator composed of both X and Z poly operators. Okay, with this, I can define twist defects. Despite recent high-profile papers calling twist defects anyons, they are not anyons. Twist defects are point-like irregularities of the code. We create twist defects by modifying the stabilizers along a line. I'll refer to this line as the defect line. So here, don't worry too much about how I've changed the stabilizers, but what's important is these are not the usual plaquette and vertex terms, vertex stabilizers of the toric code. I've changed them in some way along this line. They look just like the usual vertex and plaquette stabilizers everywhere away from this line. The twist defects are the endpoints of the defect line. So why would you want to do this? Why would you want to mess up your code in a region? Well, to help articulate why you would want to do this, let me tell you about how to actually, or the conventional method for constructing twist defects. So here's the typical approach used for topological codes, in particular the toric code. And it's composed of two steps. First, we identify symmetries of the code. Then we create a branch cut on a path with endpoints. The symmetry defects correspond to the twist defects, and this branch cut is the defect line. To make this more concrete, let's consider the toric code. The toric code has a symmetry which is built from a translation by this vector at a 45-degree angle, followed by a Hadamard gate. So here are the stabilizers of the toric code. Let's see what happens when we apply these two transformations. So first we do a translation. This translation moves the vertices to the plaquettes and the plaquettes to the vertices. So here's what happens to the operators. That product of x's around a vertex becomes a product of x's around a plaquette. These look very similar to the toric code stabilizers, but they're not the toric code stabilizers, the wrong color. So to fix that, we apply a Hadamard. So here we have it. We've mapped the toric code stabilizers back to themselves. But notice something non-trivial happened here. The vertex stabilizer is transformed into a plaquette stabilizer, and vice versa. What's happening here can be made more explicit by considering the action of the symmetry on the anyons. So let's consider the string operators for the anyons. So here's an E string operator and an M string operator, and let's apply the symmetries. So first we translate. This creates a bit of a mess. Then we apply Hadamard. And we find that the E anyons are converted into M anyons, and vice versa, the M anyons are converted into E anyons. So the symmetry swaps the roles of E and M anyons. To create twist defects, all we need to do is insert a branch cut of this symmetry. So here's what that looks like. This is where I've inserted the branch cut along this dashed line. And what that means is I modify all of the stabilizers that overlap with this branch line. So for example, here was a vertex stabilizer. This was a product of 4 poly x's. I'll apply the symmetry to one side of the line. So this poly x gets translated and then turned into a poly z. So now it's a product of 3 poly x's and 1 poly z. And that explains why I haven't included any qubits along this defect line, because those operators have been translated. Similarly, here's a plaquette stabilizer. These 3 poly z's are translated. We apply Hadamard, and they become poly x's. Now we can ask, what are the implications of this and how is this useful? Well, there are 2 interesting properties of twist defects. One is that the defect line swaps E and M anyons. This is to say that there's a string operator that creates an E anion on one side of the defect line, an M anion on the other side of the defect line, and the string operator commutes with all the stabilizers, in particular these modified stabilizers, along the length of the string. It's just like I've taken an E anion, and when I move it across this defect line, we act on it with the symmetry, and we know that symmetry permutes E and M anyons. The second property follows from this property. What we can do is we can move the E and M anyons so they're next to each other, and we have a configuration that looks something like this. This tells us that EM anyons, the fermions in the toric code, they can be absorbed by a twist defect. This is to say that there's a string operator that creates a single EM anion and can terminate on the twist defect without violating any stabilizers. So in summary, here are the 2 properties. E is transformed into M when it's moved across the defect line, and the twist defect can absorb or spit out a single EM anion. These are useful because given a set of twist defects, we can actually encode logical information. Here's a set of 4 twist defects, and I've shown that it encodes a single logical qubit. We can take the logical operators to be represented by string operators, where the logical Z operator is a string operator that moves an E anion around the twist defects on the left. And the X operator looks like a string operator that moves an E anion through the defect line. It becomes an M anion. We move it through the other defect line and it turns back into an E anion. These operators square to the identity and they anti-commute with each other. So they reproduce the operator algebra of a single qubit. So there are our logical operators. We can further do Clifford operations on this logical subspace by braiding and fusing twist defects. So for example, here's how to implement a logical Hadamard. all we need to do is swap these two twist effects. So this is great. We can introduce irregularities into the code to encode and process quantum information. Now, why don't we do this? Well, one issue is that the symmetry of the toric code involves a translation. So the symmetry defect is a dislocation. And that implies that we have to change the connectivity of the qubits in some form or another. Maybe more explicitly, notice that before inserting the twist defects, we could get away with measuring only 4-body Pauli operators. But now with the twist defects, we've introduced this 5-body stabilizer. And depending on your hardware, depending on your platform of choice, this 5-body stabilizer might be challenging to measure. It might introduce some additional overhead.
Can I ask you a question?
Yeah.
In all of this now, I mean, you are in the on the torus, right? I mean, you're not in the planar setting like in this Ted Yoder, Isaac Kim surface code with a twist setting, but it's all toric, right?
Yeah, thanks. I've assumed periodic boundary conditions here, but it's not important. We could put boundaries if we wanted to. We don't even have to, we can encode quantum information. We can use like the usual surface code, too rough, too smooth boundaries if we wanted to.
Perfect.
I'm being agnostic towards the boundaries. Yeah.
Great, thank you.
I have another question. So you showed quite nicely how you construct the stabilizers along the defect line from the symmetry action on the lattice. Do you also have a are you also able to construct the endpoint, the twist effect itself, systematically?
You mean this stabilizer?
Yeah, right.
Yeah, that's a good question. I think the best answer is that no. What you find is that there's some local degeneracy, and you find a local operator to lift that degeneracy. And this is the operator that does that.
Okay.
But maybe more intuitively, you can interpret this stabilizer at the endpoint as a loop of string operator where you take an M anion, it gets turned into an E anion. It's like a string operator that wraps around the twist effect twice. I mean, it's hard to see it, but I think that's the physical intuition. This is equivalent to, oh, sorry, my computer just decided it was a good time to sync with my iPad. Yeah, so I think the intuitive understanding of this stabilizer is you wrap a string twice around the twist effect, and then you can multiply by stabilizers to shrink it towards the twist effect, and it looks something like this.
Okay, thank you.
Before I move on, are there any other questions, comments, concerns, life advice, anything?
Did you see this paper by Riverlane a few weeks ago on measuring?
A few weeks ago.
I think so, yeah. A preprint on how to measure large weight stabilizers and yeah, I think it's about.
Yeah.
Did you see that?
I did. I haven't looked at it closely, but yeah, I am curious. Do any of you? Can you comment further on that? Do you know?
I didn't read it yet.
Okay. I mean, I think the same people have schemes for incorporating measurements of these 5-body stabilizers as part of the measurement schedule. So there are ways around this, but again, we've introduced a dislocation, so you have to fiddle with the connectivity of the qubits to some extent. But what I'd like to tell you is there's a workaround. There's an alternative way to create twist effects in the toric code, and that's by condensing anions. In the case of the toric code, in particular, we'll be condensing fermions along a path. So this will get a bit abstract, but I'd like to give some motivation for why you should expect that condensing fermions gives rise to twist effects. So first of all, what do I mean by condensing fermions along a line? We can't condense the fermions in all of 2D space. There are fermions and the statistics don't allow for this, but we can condense them along a line in the following sense. We say fermions have been condensed along a path gamma in the state psi if there exists a set of fermion string operators such that at some large enough length scale, the expectation value of the string operator tends towards a constant. So more explicitly, here Wij(em) is a string operator that creates a pair of em anyons. One is at the site I, the other is at the site j. We say that if this expectation value tends to a constant at some sufficiently large length scale, the limit of large separation between I and j, then the fermions have been condensed. Intuitively, there's some expectation value for creating or annihilating a pair of fermions at large distances. So
can you comment on
yeah?
Sorry, can you comment on the rules? So obviously you cannot just divide this W operator by the value of this expectation value, because that would be cheating. But do you understand my question?
Yeah, I don't know if I can say much about the technical rules. This is kind of a heuristic as far as a map definition goes, but you're right. Maybe there has to be some fixed norm of Wij(ems).
I mean, the point is it's not zero, right? That's kind of the...
Yeah.
Right. Like that's... I see. It's not that it tends to infinity in, like, if the defect wasn't there.
Okay. But zeros. Okay.
Thanks, Julio. Yeah.
So
okay, so why would you want to do this? What does this have to do with twist defects? Well, there are a few ways to see this, but I think for this audience, maybe the most direct explanation is in terms of fermionization. So there's a way to map a system of qubits to a system of physical fermions, where the operator algebra is generated by creation and annihilation operators satisfying fermionic commutation relations. What you see when you fermionize this system is that this string operator, Wij, gets mapped to this complicated product of creation and annihilation operators. There's some operator here. This is actually a Majorana operator, if you prefer that basis. There's another Majorana operator at the site j, and in between is a product of fermion parities. This, it turns out, the details aren't important, but what is important is that this is actually a string order parameter for a Majorana wire. So the statement that the fermions are condensed tells us that this string order parameter tends to a constant in the separation, a large separation between I and j. That tells us that the fermionic language along this path, we have a Majorana wire. So the intuition here is that the Majorana modes at the endpoints of that Majorana wire, at the endpoints of this line gamma, are precisely the twist defects in the toric code. And the defect line is the Majorana wire. That's where we've condensed the fermions. So in practice, in the context of the stabilizer formalism, how do we do this? Well, we can condense em anyons by measuring these string operators for the fermions along some path. After measuring the string operators, we're in a definite eigenstate of those string operators, so they belong to the stabilizer group. Via post-selection or making corrections, we can assume that we're in the +1 eigenstate of those string operators. If those string operators are part of the stabilizer group, that means that this expectation value is 1. 1 is a constant, last time I checked, and that means that we've condensed the fermions along this path. Now, instead of actually measuring all of the string operators along that path, we can get away with measuring just these short string operators, since those short string operators generate longer string operators. So in practice, we can condense fermions along a path by measuring short string operators for the fermions. What does the state look like after condensing the fermions? Well, in general, it's a superposition of configurations where along this path, we've proliferated fermions. So we have a superposition of all possible configurations of fermions on that path, assuming even fermion parity. Now that was fairly abstract. Let me make it much more concrete by considering the toric code. So here we have our familiar toric code. We're going to construct a twist defect by proliferating fermions along this dashed line. There are 3 steps to the construction. Sorry. The first is to define a fermion string operator along this path. Then we decompose this string operator into short string operators. These are the operators that we're going to measure. We choose these, short string operators so that they're all mutually commuting. We need to measure them, so we want them to be mutually commuting. And we want to ensure that each of these short string operators indeed create a pair of emergent fermions. So you can see this is a composition of an X and a Z Pauli operator. The X will create a pair of M's, and the Z will create a pair of vertex violations. It'll create a pair of E. So the short string operator indeed creates a pair of EMs next to each other. Now we can measure the short string operators. So after measuring these short string operators, they're generators of our stabilizer group. But if we want to include these short string operators in the stabilizer group, we have to throw away some things. The Floquet stabilizers failed to, along this path, failed to commute with those short string operators, so we have to remove them from the stabilizer group. Likewise for the vertex stabilizers. However, their product does commute with these short string operators. Here's a product of a vertex stabilizer and a Floquet stabilizer. This remains in the stabilizer group, so we may take this to be a generator of our new stabilizer group. Great. So in order to justify that this is indeed a way to construct twist defects, and we built a defect line, let me show you illustrate the 2 properties of twist defects that I pointed out earlier. First is that there's a string operator that creates E on one side, M on the other, and commutes with all the modified stabilizers along its path. And the second, which follows from the first, is that we can absorb an EM anion in the endpoint. Now, intuitively, this makes a lot of sense because I've measured this short string operator, and I've had to remove all the stabilizers that detect a fermion. So that means that I can end this string operator here, and the fermion that would be created isn't detected because I've precisely removed the stabilizers that would detect that fermion. So now let me just compare this construction of twist defects to our construction by considering symmetries. So notice we haven't had to change the connectivity of the qubits. There's no dislocation here. That's first advantage. Second, previously we had to measure a 5-body stabilizer. We don't have to measure any 5-body stabilizers via this fermion condensation prescription. Now, if you're careful, you do notice that we have to measure 6-body stabilizers. So in some sense, we've made our problem worse, and now we have to measure 6-body stabilizers all along this path. But what's nice is that this construction of twist defects will port easily over to the Floquet setting, which I'll discuss in a moment. But I'd like to comment a little further on the fact that you have to measure 6-body stabilizers. And what I'm about to say is an aside, so if it doesn't make sense, that's totally okay. It's also somewhat speculative. I ran into this over the weekend while preparing the talk, and I thought it was kind of neat, so I'd share. So notice that this 6-body stabilizer, as opposed to this 5-body stabilizer, this 6-body stabilizer is a product of our original 4-body stabilizers. That means that we don't have to, when we first put in this twist defect, we don't have to measure it directly. We can infer it from our previous measurements of the 4-body stabilizers. So now we can consider a situation where we actually wiggle the twist effects back and forth, just to avoid ever having to measure the 6-body stabilizers. So here are 3 configurations of the twist effects. And I'm telling you that we should alternate between these configurations in this order labeled 0, 1, 2, 3. And in effect, this moves a twist effect, moves the second twist effect, and then moves them back. What's nice here is that before moving the twist effect, we've been measuring the 4-body stabilizers. We move the twist effect and we get the 6-body stabilizers for free, because those are products of the 4-body stabilizers. Then, after we've moved the twist effects, we resume measuring the 4-body stabilizers and move them back. So in this way, we never actually have to directly measure any of the 6-body stabilizers. We're always able to infer them from our 4-body measurements. I think the right interpretation of this is as a small instance of a Floquet code. We're wiggling these twist effects back and forth in a periodic fashion and inferring all the stabilizers that we need from our instantaneous stabilizer groups. Okay, well, that comment might have been somewhat unclear. I haven't introduced Floquet codes, so let me introduce Floquet codes now. Before I move on to discussing twist effects in the context of Floquet codes, are there any questions or comments, riddles, anything?
Maybe a quick comment. There's a quick question now that you're on this wiggling slide. Is there something else that trades off against this? Like, am I losing something in the distance of the code or something like that by doing this wiggle?
Well, you're avoiding measuring a 5-body stabilizer by introducing extra qubits so that you can have room to wiggle your twist effects. So something that you're losing is now you've avoided having to add an ancilla to measure your 5-body stabilizer, and added a bunch of other ancillas so that you can move your twist effects. So whether this is practical is another question. I don't see any sacrifice in code distance in wiggling the twist effects, but I would really need to stare at it further.
Thanks.
I've got. You can go ahead.
Okay. A small question on how I can see that measuring the short string operators really create this defect line. If I understood correctly, we know how the defect line should behave in terms of anyons. So it should swap E and M, so the fermion should just be able to pass through, right? But when you measure, and it should only be able to condense at the endpoints, or like the string operators for the fermion should only be able to terminate at the endpoints. Am I missing something, or is it possible for these fermionic string operators to also terminate along the defect line for in the setting that you showed when you measure the 2-body terms along the line?
Right. So you can definitely end the fermion string operator at the twist effect, but there's an obstruction to ending it along the defect line. And that can be seen from recognizing that in order to compute the statistics of fermions in this microscopic level, you use some T-junction calculation. You have string operators meeting at the intersection in a T-junction. And if you were to end a string operator on the defect line, that's exactly what you'd have. So now you're asking 3 operators to commute when you know they shouldn't all commute because you have a fermion and you should get a -1 sign from somewhere.
It's always kind of 2 of these hopping terms and then half of one sees the fermion string still. Yeah, I think I see it microscopically now.
Yeah.
Okay, cool.
So I was wondering, how do you know whether your short string operators are long enough? Because like in principle, a single X could also be seen as moving a fermion. It only moves the fermion like from like one side to another side, but the sides share the same vertex but different plaquettes. But obviously that doesn't work if you measure individual C's and X's. So how do you know that like an X and a C is short enough?
Yeah, it's somewhat ambiguous, right? But I think our rule of thumb, our working understanding is that that short string operator should violate the right stabilizer. It should actually create a pair of emergent fermions. Now, the emergent fermions are kind of ill-defined on such a small length scale, but in your example where you have just a single X, it does create M's, just a pair of M's, and it's not really clear whether
microscopically it's like there's no anions, right? It's only in the limit of long separation. But is it true that if I have like that there's like some length such that if I measure like anion ribbons of that length, then this will always work? Like if you were to measure like say distance 3 short string operators, that would also work, right? That would just give a very ugly code, but like theoretically that would give the right phase. Then is that true?
If you believe this anion condensation picture that I painted, the answer is yes. I would need to think about the microscopics some more. I remember there being an issue, but on the spot that sounds believable.
So you're saying it could be that they can also be too long, and that's also not good?
You know, I don't have a good answer to that. I want to say that makes sense. You can just choose the string operators to be longer, then you have well-defined fermions, and at least from this fermion condensation picture, you are indeed condensing fermions. But maybe I'm getting confused with another problem we ran into, but I'm hesitant to say outright that will work at a microscopic level. I'm confused about something at the moment.
Have you looked at what happens if you like go around a corner? Can you then like measure a single Z on a vertex at the corner?
Yeah, so in some cases you can get away with measuring just single body operators. Now, if I worked in the rotated surface code, there's a string operator that's composed of just poly Y operators. So what that looks like is just like Y operators along a diagonal.
Yeah.
And in that case, you can create the twist effects just by measuring single body Y operators.
Yeah, makes sense.
So there are some cases where you do just measure single site operators. But the claim is that there's always a way to decompose this in such a way that the short string operators commute and they create fermions. And I think that's our safest bet. But I haven't really explored what happens when you fiddle with this precisely.
Cool. All right. Thanks.
Yeah, good questions. Thank you. Oop. Okay, so now I'm going to discuss finally twist effects in the Z2 Floquet code. The Z2 Floquet code is also sometimes referred to as the honeycomb Floquet code, or maybe you prefer to call it the Hastings-Hoff Floquet code, or you're feeling real rebellious and you call it the honeycomb dynamical automorphism code. I just chose out of a hat to call it the Z2 Floquet code. So today I'm calling it the Z2 Floquet code. I might have to remake these slides all tomorrow. Anyways, it's the same code. So what is the Z2 Floquet code? In order to describe the Z2 Floquet code, let me make some general comments about Floquet codes. So, sorry, mute myself. So in general, Floquet codes are dynamical quantum error correcting codes where the code space evolves in time according to a periodic schedule of measurements. So here's an example where we have 3 rounds of measurements labeled 0, 1, and 2. And if you follow I'll assume that these measurements are measurements of Pauli operators. And if you use the usual rules for how to update the stabilizer group after making Pauli measurements, you see that at each instance of time, we have an instantaneous stabilizer group, sometimes called an ISG. Each of these instantaneous stabilizer groups has an instantaneous code space. We store quantum information in that code space and schedule the measurements in such a way the information is preserved throughout the dynamics. I'll also allow for some initialization just to get the ball rolling. And after this initialization, then the measurements are periodic. So what do I need to tell you to specify a Floquet code? I need to tell you two pieces of information. The first is I need to tell you what gets measured. That's true for any error correcting code, classical or quantum. I have to tell you what to measure. I'll refer to these as the checks. The second piece of information that I need to specify is when to measure those checks. In the Torah code, this wasn't an issue. The checks are mutually commuting, so you can measure them at any time you want. But here, generically, the checks fail to commute with one another, so you have to be careful with your measurement schedule. Let me make this more concrete now with the Z2 Floquet code. The Z2 Floquet code is defined on a hexagonal lattice with a qubit at each vertex. To specify the checks, I'll label the edges by X, Y, and Z. X edges have positive slope, Y edges have negative slope, and Z edges have 0 slope. The checks on the X edges are a product of poly X operators. On the Y edges, it's a product of poly Y operators. And on the Z edges, it's a product of poly Z operators. So what's cool here, in contrast to the toric code where we have to make 4-body measurements, here I'm telling you that all we need to measure are 2-body operators. If you are working with a platform that can natively make 2-body measurements or have limited connectivity of your qubits, this might be a big advantage. So here are the checks of the Z2 Floquet code. The next piece of information is when to measure these checks. You'll notice that these checks, if they share a vertex, they fail to commute with one another. So the order in which I measure these checks matters. In order to specify the schedule, I'll label the plaquettes by 0, 1, and 2 in such a way that neighboring plaquettes never share the same label. I'll then define the 0 checks to be the 2-body operators supported on the edges that connect between the 0 plaquettes. Those are all shown in red here. These are edges connecting between 0 plaquettes. Likewise, the 1 checks connect between 1 plaquettes, and the 2 checks connect between the 2 plaquettes. As you might have guessed, the schedule is to measure these in sequence, 0, 1, 2, and then repeat.
But you're not doing 0, 1, 2, 2, 1, 0, 0, 1, 2, 2, 1, 0, which might be an advantage when you think of boundaries or so.
That's right, yeah. Right now, I'm just assuming periodic boundary conditions.
Okay.
But you're right, depending on what you want to do at the boundary, you might need to rewind your Floquet code. You might need to reverse the order of the measurements just to have consistent boundaries. But again, I'm being agnostic towards the boundaries. When you're introducing twist defects, as long as those twist defects are far from the boundary, you can use whatever measurement schedule you want at the boundary. Assuming those twist defects are far away from the boundary, you won't run into any issues with fault tolerance. So here's the Z2 Floquet code. You measure these 2-body checks in the orders 0, 1, and 2 and repeat. There's some initialization, but let me not get into the details of the initialization. The ISGs look like this. After I make, just to help walk through what these ISGs look like, after I make the 0 checks, since I just measured those operators, those will definitely be part of the instantaneous stabilizer group. So the 0 ISG includes these 0 checks. Then I measure the 1 checks. In general, the 1 checks fail to commute with the 0 checks, so I have to remove the 0 checks. And now I include the 1 checks in my instantaneous stabilizer group. But notice that there are products of 0 checks that do actually commute with the 1 checks. In particular, you can take a product of 0 checks around a 2 plaquette, so it's these 3 red edges, and you can check that those 3 check operators commute with your 1 checks. So we have more than just the checks in the instantaneous stabilizer group. We also have these plaquette stabilizers. Now, given the conventions that I chosen, these plaquette stabilizers are homogeneous. They all look the same for 0, 1, and 2 plaquettes. They're a product of X, Y, and Z operators around the plaquette. What Hastings and Haas showed is that these instantaneous stabilizer groups are locally equivalent to toric codes, in the sense that there's some, using Ancilla, there's some local unitary that maps the stabilizer groups to the stabilizer group of a toric code on a hexagonal lattice. We still have a vertex term, it's a product of X's, and a plaquette term that's a product of Z's. What that tells us is that each of these instantaneous stabilizer groups are characterized by the same anion theory as the toric code. The EM and EM anions might have different interpretations. There are no clear vertex and plaquette stabilizers in this case, but nonetheless, we can associate violations of stabilizers to the anions of the toric code. This also tells us where we're storing quantum information in this code, because at each instance in time, we have a toric code. So if I were to have periodic boundary conditions, we're toggling between these 3 toric codes, and we can write down representations of the logical operators that look like string operators that wrap around non-contractible cycles. So this is all I'd like to say about Floquet codes. I'm now going to tell you how to construct twist defects in the Floquet codes. But before I do that, are there any questions, comments, concerns?
Yeah, can I
Moments
just
of silence? Yeah.
This slide?
AT?
What
Yeah.
are the what are the differences between the 3 different ISGs? Just a color change, and what does it mean?
What are the differences?
Sorry.
Let's see.
Yeah.
No, you're right. You're right. I just changed the colors. That's supposed to represent the fact that these string operators are, in general, different products of Pauli operators.
Okay.
And you'd have to write down the string operators for EM and EM for each of these ISGs. And you see that they aren't the same string operators. There might be some overlap between ISGs, but in general, there'll be different operators. And so I tried to represent that with changes of colors, but yeah. Yeah, thanks for asking.
So is it actually a 3D toric code that it's equivalent to? Like if I look at your stabilizers on the previous slide.
Is it a, sorry, well, the question was, is it a 3D
Oh, sorry,
toric code?
no, sorry, I see, it's something.
Yeah, it's all in 2D, it's on a
Sorry.
hexagonal lattice. That's right.
Yeah.
No, yeah, thanks for asking. Yeah, this is all on a hexagonal lattice. It's 2D toric codes.
Okay.
We have a different instantiation of a 2D toric code at each instance in time.
Great, thanks.
Yeah, good, thanks. Okay, let's construct some twist effects. We could go about our construction of twist effects by first identifying symmetries and then inserting symmetry branch cuts, but it's not at all obvious to me how to go about this. So the first ambiguity is, do we identify symmetries that are shared by all of the ISGs? Do we just consider symmetries of one of the ISGs? I haven't been able to find any zero form symmetries, so symmetries that act in all of space that are common to these ISGs. So it's not clear that there's a way to insert a branch cut consistently between these ISGs. You could insert a branch cut in one of these ISGs, but that'll look like just a mess in the subsequent ISG. So our conventional approach to building twist effects doesn't apply in any obvious way. The resolution is to use an alternative approach to constructing twist effects, and that's to condense fermions along a path. And I should have called this, I've unfortunately called this a one-form symmetry. All I mean is that we recognize that the plaquette stabilizers are common to the ISGs. These plaquette stabilizers can be interpreted as small loops of fermion string operators. And these generate a symmetry group, sometimes referred to as a one-form symmetry. All the symmetry operators are supported on loops. But the point I'm trying to make is that because these loops of fermion strings are common to all of the ISGs, the string operator that creates a pair of fermions will create a pair of fermions in each of the ISGs. So we can use the same string operator to create fermions at each instance of time. So here's how we construct twist defects. It's embarrassingly simple from here on out. All we need to do is follow our nose, and there's not much more to it. So how do we do this? Well, first, I'll define a fermion string operator. How did I write this down? Well, one way to write this down is to take a product of the plaquette stabilizers. If you believe me that those create a fermion string operator along the boundary, then you can truncate. You can just throw away most of the poly operators, and you have a segment of fermion string operator along a path. In this case, it's a product of poly Z operators. The next step is to decompose the string operator into short string operators that are mutually commuting. And we'll require that those short string operators create emergent fermions in each of the ISGs. It creates a pair of fermions in each ISG. Then, instead of modifying the stabilizers along a path, as we usually do to create twist defects, we'll modify the checks along a path. We'll add these two-body operators. I'll refer to them as defect checks. We'll add these defect checks to the set of check operators. Now notice that we haven't made any compromises here. We still only need to measure two-body operators to do all of our error correction. But to have an interpretation of condensing fermions along this path, it's not enough just to include those two-body operators as check operators. We actually need to ensure that they are stabilizers. So to do that, we'll throw away the checks that fail to commute with the defect checks. So we measure the same set of checks, except we throw out the checks along the path that fail to commute with our defect checks.
But and you're claiming that you're still getting the same twist effect in this fashion.
I'm claiming that in each ISG,
Yes.
you can interpret this as a twist defect.
Okay. Yes, that's a more precise way of putting it. Yes. Okay.
And I'll show in a moment that we can reproduce the properties that we expect from twist defects. E gets turned into M in an instantaneous stabilizer group. So it is indeed a twist defect.
I see. Okay.
Yeah. Okay, so you're right. All we need to do is make a pretty modest change to our checks and our schedule. The initialization is the same. We can initialize without any twist defects. Then we insert twist defects by measuring the checks 0 star, 1, and 2. Here 0 star includes the defect checks. It includes these ZZ two-body checks. I chose to include it with the 0 checks at random. By construction, the defect checks commute with all of our checks, so we can measure them at any point in the schedule, but might as well just lump them together with the 0 checks. Now to address Jens's question, let's just consider.
It absolutely does.
Yeah, sorry?
Yeah, I'm happy.
Yeah. So let's just consider the 0 ISG. So here we measure the red checks and the defect checks. Here's what the instantaneous stabilizer group looks like. So we still have the plaquette stabilizers away from the defect line, but along the defect line, we have to modify the instantaneous stabilizers. Just like we modify the stabilizers of the toric code, here we modify the instantaneous stabilizers. You'll notice that these defect checks individually fail to commute with the plaquette terms along the defect line, but they do commute with a product of plaquette stabilizers. And we never have to measure this product of plaquette stabilizers directly. We can infer that from our measurements of two-body stabilizers. Okay, so here's the ISG. You can check that there's a string operator that creates E on one side of the defect line and M on the other side of the defect line. So we really do have a defect line that permutes the E and M anions. So now we can talk about how to encode quantum information. By inserting twist defects, we can also use the standard procedures for processing quantum information by braiding and fusing twist defects. So let me just summarize some of the benefits here. First of all, it can be constructed in a planar geometry. So we could also add boundaries to this story and just encode more logical qubits by creating twist defects. We haven't had to make any changes to the qubit connectivity, in contrast to the approaches taken to create twist defects via dislocations. We've maintained the property that the Floquet code operates entirely off of two-body measurements. And depending on some subtleties at the boundary, we maintain the 3 round per period measurement schedule of the Floquet code. So I'm running out of time here. Let me conclude with some further comments that I didn't have time for. I'll restate the main takeaway and then go over some future directions. So here are some further comments. We've also generalized this story to Zn Floquet codes. Zn Floquet codes are defined on n-dimensional qubits. The instantaneous stabilizer groups are locally equivalent to Zn toric codes. So there's a richer anion theory that describes the ISGs. And as a consequence, there's a richer set of twist defects that can be created in those models. Now, instead of just condensing a fermion, you can consider condensing other types of anions. One consequence of this is starting with the Z4 Floquet code, whose instantaneous stabilizer groups are the same as a Z4 toric code. We can create a Floquet code with ISGs that are characterized by double semyon anion theory. So what we do is we take our Z4 toric code, we condense a particular boson in a grid pattern in such a way that some of the anions are confined, others are deconfined, and the deconfined anions are precisely those of a double semyon topological order. Let me mention that Andy also has a construction of a Floquet code with ISGs that have double semyon topological order. The last thing I'd like to mention on this slide is that we have another work in which we construct examples of 3D Floquet codes. One is a natural generalization of the Z2 Floquet code. The lattice is kind of complicated here, so don't bother staring at it for too long. But the point is that the instantaneous stabilizer groups have the same topological order as a 3D fermionic toric code. This is like a toric code, but the point-like excitations are fermions. Since we have fermions, we can condense them along a path, and we can insert twist defects in this 3D code.
Is that a fermionic like model with like fermionic degrees of freedom? What do you, but what do you mean by 3D fermionic toric code then?
Yeah, this is maybe unfortunate nomenclature, but
Okay.
This is just what we've been calling it amongst ourselves. Fermionics distinguish it from the toric code. The usual toric code has a point-like boson. Here by fermionic toric code, I mean like there's a point-like fermion.
So it's just a 3D bosonic topological phase that you call fermionic toric code?
Right, yeah.
Cool. And it only has
called a twisting toric code.
Okay. And it only has like one fermionic point-like excitation.
Right.
Cool.
But wait, that is already a twisted toric code.
There already is a twisted toric code?
Yeah, it's this fiber bundle code.
Okay, well, that's why we called it the 3D fermionic toric code. Yeah. Okay, so let me tell you the main takeaway, and I'll just flash some future directions. So again, the main takeaway here is that we've introduced a method for storing and processing quantum information in Floquet codes by creating twist defects. We build those twist defects by a somewhat new method, and that's by condensing or proliferating emergent fermions along a 1D path. All right, here are some future directions. Our setup is quite natural to implement on one of IBM's processors. IBM's qubits are arranged in a heavy hexagonal lattice. There are qubits on the vertices and also on the edges. The qubits on the edges can be used to make as ancilla to make these two-body measurements. Furthermore, something that I think is somewhat interesting is that one of the issues with IBM's hardware is that sometimes the coupling between qubits is it's broken and doesn't work. Well, that works well with our procedure here because we had to throw out some two-body checks. So we don't make any measurements between those qubits. So we can actually use the defects in the hardware to build our twist defects and use their inherent defects to encode information. The other project that I'd like to comment on is in collaboration with Larry and Dom at the University of Sydney. We're trying to develop an understanding of twist defects from a space-time perspective. Now, instead of condensing fermions along a path in a spatial slice to construct twist defects in space-time, we think the right interpretation, following from some work from the high energy commuting on higher gauging, the right interpretation is to condense loops of fermion world lines along a membrane. Then, when you consider a particular instance in time, you intersect this membrane along a path, and from the perspective of this path, you have open string operators for fermions, so that then you recover this picture where you're proliferating fermions along a path. Okay, sorry I've gone 4 minutes over, but thank you for being patient, and I'll stop here.
Wonderful. Thanks for the very clear talk. That was very insightful. We had lots of questions along the way. Maybe there's more.
I have a, so thank you first to also accept my invitation to give the talk again. Yeah, I have a small question on the details of the two-body terms along the defect line. So the way you showed them, they were all arranged vertically. And if I catched it correctly, this is the reason why you only need to measure Z operators, right?
Yeah, it's the particular orientation of the string.
Yeah.
If you change the orientation, you might have to measure mixed products of Pauli operators like X and Y or Z and X, something like this. Yeah, it's orientation dependent, at least in this convention using the honeycomb code.
Did you also look at like code deformation things, like to break the defects in a dynamical setting? How long do you need? Can you do it within your schedule or yeah?
Yeah, so I think, you can do this in a very similar fashion to the way people usually think about moving twist defects in the toric code. And what that looks like is at some instance of time, you might be measuring a configuration. Maybe I have a picture here. Possibly not, but at some instance in time, you're measuring one configuration of twist defects. At another instance of time, you measure a different configuration. That's your code deformation. Maybe it's like a Floquet code deformation if you really want to call it that. And there's some sequence of moves that you can use to braid or fuse twist defects. And it takes some time because after you move these twist defects, you may need to do D rounds of measurements just to make sure that everything's fault tolerant and that in space-time, the world lines of the twist defects aren't getting too close to one another. But yeah, we have some commentary on this in our paper and in an update that will hopefully happen soon. I'm hoping to add some more words about this. But yes, there's some procedure for doing this, but there is some time overhead that scales like the code distance.
May I ask? You said
Yeah.
this construction preserves the property that there's only 3 rounds in this code, except at boundaries. You said, is that just because of the usual boundary thing, or is this an extra complication from terminating your kind of stuff at the boundaries?
Yeah, so it depends on what you want to do at the boundary, and it depends on how much space you have. So what we've found is that if you extend this schedule to be 6 rounds per period, then you can put the twist defects anywhere you'd like on the chip, and it's still fault tolerant. If you want to do everything in 3 rounds of measurements, you can do that. But in order to make sure that it's fault tolerant, you have to have the twist defects and some distance on the order of the code distance from the boundary.
Okay.
So there's some funny, if you have 3 rounds of measurements, there's some funny business that happens at the boundary. Boundaries like switching between E and M or rough and smooth type boundaries.
Yeah.
And to avoid some sort of constant weight logical operator, you have to keep the twist defects far from the boundary. So you can do 3 rounds of measurements with the caveat that you have to have some buffer region.
But the buffer region is the distance, or like a constant times the distance? Because this is pretty heavy.
Yeah, some constant times the distance, yeah. Yeah, because the errors look like they have to be like an E anion that shoots out from the boundary. You miss it for a couple of time steps, and then it gets reabsorbed into the boundary at some later time, something like this. And yeah, so it maybe has to travel that distance twice and be missed by some measurements. So, you know, I don't know what that constant is exactly, but I'm guessing less than 1.
Interesting.
So yeah. I didn't get the one point where you like threw away some of the checks. So I think you said you have to kind of not like throw away these checks that live on the same line, but do not commute with the ones measured. But like, is there like a deeper meaning between this rather than just like that they live on the same line in the picture that you happen to draw? Or?
Well, usually when you condense fermions, you have to throw away some stabilizers. Yeah. So it's not outrageous that you have to throw something away. And
yeah. But you don't throw away every stabilizer that doesn't commute with it, right? You only throw away some.
You end up throwing away all the stabilizers that fail to commute with, indirectly, you throw away all the stabilizers that fail to commute with your defect checks. And it's indirect because what you're doing is actually throwing away some of the checks.
I see. Okay, so you throw away some of the checks, and you look at your ISG, and then you see that this does the right thing.
Yep, and then you get something like this. So along the defect line, you have this product of 2 plaquette stabilizers that survives. You never measure the individual plaquette stabilizers because you've thrown away that check.
Yeah, that makes sense. Okay, cool.
Yeah.
Cool. And again, the short string operators, you can't make them an individual C, but like 2 C's is kind of the shortest element that you can get in a way. Okay.
Yeah, so I tried. And what happens if you make single body measurements is that in the instantaneous stabilizer codes, they create E or M anions. And so it's like you're just punching a hole. It's like a E condensing or M condensing hole, and it might change from E to M over time. But yeah, you aren't getting a defect line. You don't have this property that I've shown here on the slide.
Yeah. Cool.
Yeah. So since you mentioned punctures, so can you also do something like wormholes in this setting? So like an object that looks similar as like a, what is it, combination of twist defect and puncture, but in a way that like a logical string can go into one twist defect and then doesn't condense, but gets like, you have to go out on the other side again.
So just to clarify, the wormhole picture you have in mind is you make some like distant measurements. Yeah, that's a good question. I haven't thought about this.
There are also, so I think the original proposal was already to effectively do this long distance measurement, but in a protocol where you only do nearest neighbor measurements along a line connecting the 2 punctures.
Okay, yeah.
But I don't
guess
know
I'm
the
not-
details myself, so maybe
Yeah, that's interesting. I haven't thought about that much. And yeah, maybe I need to expand my horizons and stop thinking locally. Maybe there's more to be said. Yeah.
Exciting.
Yeah. Well, thank you. Thank you for the questions.
If all the
Sorry.
serious questions are gone, may I quickly ask that photo of Larry that wasn't a photo of Larry? What's that about?
Oh, sorry. Yeah, I asked Larry if he had a photo, and he said he didn't have any headshots. So
Okay.
this is actually a picture of the emblem on their Slack page for the quantum theory group at Sydney.
All right. Okay. Cool. Thank you.
Yeah.
Funny.
Yeah.
Good. Thanks for
Yeah.
the talk. Thanks
Larry's
for
not a robot. Yeah.
that was wonderful. Very clear, very instructive and
Thank you.
educational. Very good. Thanks for the time and contribute to the flood of Floquet codes. Yeah, see you around. Thanks to all and more soon.